Welcome to the next video in the Let's Calc series. In this video, we're going to be focusing on the problem set devoted to infinite limits, and in particular limits that have values of infinity, and specifically how to handle things like vertical asymptotes and things along those lines. It's a pretty short lesson. In fact, it's a really brief lesson. It contains a lot of stuff you've seen before, but I still wanted to cover a few things, talk about some little wrinkles that get thrown in that maybe we didn't address in the past, and look at some of the harder questions that are covered on this assignment. There is one particularly meaty word problem that I'm choosing not to cover, and it's simply for copyright reasons because it is related to a very public organization, and I don't want them to chase me down on YouTube. So I'm skipping that question. Sorry, you can see very carefully written solutions in the written problem set solutions. So without further ado, let's jump into the first question. Let's do this right this time. Boom. Okay, the first question that we're going to look at here is going to be question number 6. It comes from the first section of the assignment, and the first section of the assignment focuses on vertical asymptotes. Now I realize you've done work with this in the past, so we're not even really applying that new definition in any way. It's just an opportunity to revisit a little bit in light of the formal definition that was finally provided in this lecture. So the instructions say to find the vertical asymptotes of each function, if any. So the assumption is some of these functions will have vertical asymptotes, some will have none, some might have an infinite number of vertical asymptotes in fact. And out of those, the first 5 I felt like were pretty straightforward, but number 6 features a little bit of a wrinkle. It actually features a couple different wrinkles if we're being honest. So let's take a look. The function in question is a ratio of a linear function, y equals x, and a trigonometric function, y equals sine x. So in this case, typically, when we're looking for vertical asymptotes, our typical focus mean that we look at where the denominator, which in this case is sine of x, is equal to 0. That's always our focus. Now sine of x is equal to 0 at x equals pi k, where k is an integer. In fact, we've done a problem like this before, so nothing particularly wild about it. In fact, I'm hoping you still remember that very thing. So that would be great, and I know it's tempting to just box that answer and go from there and say that we're done, but there's actually a unique thing that's here. This function is not just cosecant of x, which would absolutely have vertical asymptotes at all of those x values. This one has something else, and that something else is that numerator of x. So if you look at the numerator, x equals 0 makes the numerator equal to 0, but that also means that sine of x is equal to 0, because x equals 0 and sine of 0 are both simultaneously 0, which means that this is our answer, except for one exception. At x equals 0, it appears that since the numerator and denominator both go to 0, we have an indeterminate form, suggesting that we actually have a whole. Now we'll look at Desmos in a second to see if that actually plays out that way, but for the moment, we want to be able to communicate this and write out our stuff. So if we wanted to write out our vertical asymptote places, there are a number of ways that we could attack. We could say that vertical asymptotes are at pi k, where k is a non-zero integer. In fact, that's probably an ideal way to say it if you don't know any further mathematical vocabulary to go with. There is one other way that you could say it, although I do like that particular answer. You could say instead that instead of x equals pi k, you could say that x equals plus or minus pi times n, where n is a natural number. And I bring this up just because it's one of those like small, I'd say it's like a weak spot in like the mathematics education, at least as far as I can see, is we oftentimes forget about the different types of numbers that are out there. Like we talk about rational numbers, which can be presented in a certain way, or irrational or imaginary, but natural numbers, so like natural numbers, which are often represented with this symbol, the natural numbers are the set 1, 2, 3, 4, etc. It's oftentimes called also the counting numbers. So in this case, what we're trying to say is that we want to exclude 0, but have all the other integers in there, all the other positive and negative integers. So if we say n is a natural number, that gets us 1, 2, 3, 4, 5, 6, 7, 8, all those things without including 0. And by putting a plus or a minus, we also get all of the negatives of those things, conveniently excluding 0. So in a sense, this one's just kind of an interesting question. 1, because of that interesting behavior that occurs at x equals 0. 2, because just communicating what those x values are where we have vertical asymptotes is somewhat difficult. Now, as promised, I said we'd take a look at Desmos really fast and see if this looks about right. So let's graph in there really fast. Y equals x over sine of x. So in here, we're supposedly going to have vertical asymptotes at lots of pi values. x equals, let's go pi times n. They want to do, oh come on, just let me have my n value. X plus b x, there we go. I want n to be that. Ignore that thing, that's just a trick to get Desmos to follow my instructions. So if we look here, we'll go from 0 to 6, steps 1. Let's just see if this looks about right. Do we have all those lines are representing asymptotes? It looks like we're accurate there. But notice at 0, there's definitely no asymptote. Now, technically at 0, you can see it just for a second. 0 gives us an undefined value, of course, but you can tell that there's definitely not a asymptote right there. In fact, it looks to me like the limit is actually equal to 0, 1. Or the limit is equal to 1. So for the moment, though, what was important was that we could see that this does seem to have an infinite number of asymptotes. A little different. It's scaled a little differently. It's actually kind of cool, by the way. Y equals, if you're curious about those things, there's an asymptotic sort of behavior going on here too, which is kind of neat. But beside the point. In any event, what I wanted to show you is that this one does in fact not have a vertical asymptote right there, which is just kind of interesting. Definitely a little more challenging than the average question. And there completes our work on number 6. That takes us, though, to question number 9. Question number 9 is kind of the standard vertical asymptote type question, but it's elevated quite a bit. This one isn't just a simple function where you can just quickly sketch everything just like normal, and it's easy, and you figure it out really fast. This one involves a multiple vertical asymptote situation, and then asks us for a one-sided limit, so at least that's there. So really the focal point on question number 9, in which we are instructed to evaluate the limit and show any sketches or computation, is for us to meet the challenge of actually sketching this function 10 over x squared minus 9. So to start with, before we jump in, I just want to rewrite this in that factored form so it's really clear what it is that I'm going to be trying to graph. We'll have 10 over x plus 3, x minus 3. Of course, there is our thing. So we need to graph this function. So I'm going to do a sketch right down here. And again, not the world's best artist, obviously. Like, how many people are in the world? 8 billion? Probably roughly in visual art. I might be in the top, I don't know, 7.9 billion? I'm not sure. But in any event, there's everything set. So we want to sketch this function. So what I notice is that this function has, actually I'll write this down here. This function has vertical asymptotes at x equals plus or minus 3. So there are 2. Graph 1 right there. I'll graph 1 right there. And now I need to describe the rest of the behavior. So there's a couple things in here that make this tough. First, we haven't talked about limits at infinity yet, but I'm hoping you can recognize that since the degree of the denominator is higher than the degree of the numerator, that means that we're going to have a horizontal asymptote, of y equals 0. So specifically, we'll have a horizontal asymptote right there. And now the old phrase they used to use in Algebra 2 was hug your asymptotes, but before we do that, we need a few more points of context. So a couple things. We'll find a couple intercepts here. First, we'll look for the y-intercept. That's always a good point. That means we're going to plug in 0 and get some number. So in our case, that's going to be 10 over 0 minus 9, 0 squared if you're counting at home, which is negative 10 over 9. So a negative number is right down here. So we have 1 point. We'll play with the rest in a second. For x-intercepts, though, we need to set the numerator equal to 0, at least after any factoring and dividing out. So the numerator is 10, so we need to figure out when does 10 equal 0. And the fact is that's not true. So what that means is there are no zeros for our function. There's never a place where this graph crosses the x-axis. So with that in mind, looking at our picture, we can predict at least some behavior. First, since we can't cross and get some sort of 0, our graph can't do anything like that. It must stay below the x-axis. So in the middle section, we should have a picture that looks along those lines. Now in this case, that's actually enough to finish our problem. We were asked to limit as x approaches negative 3 from the right side. As x approaches 3 from the negative 3 from the right side, we get negative infinity. So in fact, there is the limit that we were looking for. We don't even have to go any further. Oops. If you're interested, though, in figuring out how to graph the other portions of this graph, there are a couple different ways to get there. But the safest way is to find 2 more points on your picture and see where they actually fall. So for instance, I might choose to put in the point, let's see here, I know, let's put in the point, let's put in 4. So if we do x of 4, here, let's just do it this way, this is being silly. So do 4 squared minus 9, we get 10 over 7, which is positive. So in other words, we have a point at 4 comma a positive number, which means that that's somewhere like right here, which means this section has to hug the asymptotes and stay in that upper corner. And likewise, if we go to the left, we can plug in negative 4, and we'll have 10 over negative 4 squared minus 9, which is clearly going to have the exact same value and be positive as well. So that point would fall right over here. We'd have something along those lines. So that would be our whole shape. With that in mind, we could attack any one-sided limit around those asymptotes and see whether the function goes to positive or negative infinity. But for the moment, all that really mattered was that first chunk, which we were able to find pretty quick. But definitely some advanced rational function graphing skills necessary here. Might need to crack out Graphidash at some point, in fact. So hopefully that clarifies a little bit of your work on number 9. And the other questions in that section often involve similar quick visual and graphical work. That brings us to question number 11, which looks like a super souped up version of the last question we attacked, number 9. So in this case, we have a quadratic polynomial over a cubic polynomial, and we're taking the limit as x approaches 5 from the left side. So this looks like this could be a problem. But we don't necessarily have to go that. Like, let's play it safe. Here's kind of my thought here. If we plug in 5, like, oh, okay, let's pretend for a moment that we don't recognize that you could try direct substitution here. So let's say that instead we simply start factoring this mess. So the numerator, pretty easy. Quadratics are pretty straightforward. In the denominator, we have x cubed minus 5x squared plus x minus 5. So what I'm going to do is I'm going to factor this out. This is a grouping technique polynomial. You may have used the box when you were there. You may have used something like this. There's lots of different ways to get there. What I see when I look, though, is I see x squared, x minus 5, and plus 1 x minus 5. Typically, I don't even do this line, by the way, but that's true. And then this tells me it factors to x minus 5, x squared plus 1. So with that in mind, no matter how you get there, we have x squared plus 1 times x minus 5. Now something interesting happens here. We were expecting a vertical asymptote just because that's kind of the general theme of this page, or it's a nice motif along the entire assignment. But we have x minus 5 in the numerator and x minus 5 in the denominator, which means that we have a hole at x equals 5. And not only do we have a hole, but we should have that the limit exists. From both directions, it should be approaching the same y value, because that was getting an indeterminate 0 over 0 form because of that x minus 5 that we just divided away. What that means is our limit, as x approaches 5 from the left side, is actually going to be evaluating the same limit for x over x squared plus 1. And in this case, that's going to be equal to the limit as x approaches 5 from either side. It's not going to change our behavior. So we can just direct substitute in, and we'll get 5 over 26. So in this case, the trick or the twist of the question was you weren't actually being given something with asymptotic behavior. You just thought you might. So being careful here allowed us to easily look at this function and treat it just like any other, and we could go through and actually determine what this was. Now, just to illustrate that this is true and that I haven't been fooling you, let's graph this function really fast. Y equals x squared minus 5x. I think it was x squared plus 1. I should do this properly. X cubed minus 5x squared plus x minus 5, I think. Was that the right function? Let me make sure I did this right. X cubed minus 5x squared plus x minus 5. There it is. So now we were interested in what was happening at x equals 5. So notice as it says right on here that at 5 the function is undefined, but clearly there's a limit there. And since we got the point 5 comma 5 over 26, yeah, that looks pretty darn accurate to me. Looks like we found the correct limit. So there you go. An interesting problem, but evaluable using the normal stuff that we do. Okay, that next brings us to question number 12. And question numbers 12 and 13, questions number 12 and 13, focus on particular types of functions, specifically even and odd functions. So we're talking about those once again, just kind of choosing to go over them once more, just to keep reminding you that they're there, because it's something that will show up at some point. So in question number 12, it states first, let d of x be an odd function. Then it says if the limit as x approaches 6 from the right side of d of x is equal to infinity, what is the limit as x approaches negative 6 from the left side of d of x? So now, if you'll recall, odd functions have a particular truth about, there's a particular piece in their definition. So if a function d of x is odd, that implies that if you plug in negative x to d, you're going to get negative d of x. So there is, by the way, a way that you could attack this problem using that particular method. But instead, in this case, since it doesn't ask us to explain or justify our answers, what I'm going to use is simply my visual skills. I'm going to just try to sketch a graph of this situation and see what would happen if the function is odd. So first of all, we're talking about odd. We talked about what that means on a definitional level. Let's think about what this means visually. An odd function would be something like the cube root, where there's a symmetry like this. There's a symmetry, a rotational symmetry about the origin, or like it's been reflected once and then reflected twice. Same different thing. So with that in mind, let's sketch a situation where we have this set up. So at the limit as x approaches 6, so I'm going to draw x equals 6 right here. As we approach from the right side, so we're coming from this way, we should be approaching infinity. So here is a scenario where approaching from that direction takes us to infinity. So we wanted to talk about what's happening on this odd function at negative 6, and we approach it from the left side. Well, because of the rotational symmetry that happens here, if we have a point, I don't know, let's say this is the point 7, 7, then we have to have a point down here, which would be at negative 7, negative 7. So in other words, following that pattern, the graph must basically be almost reflected across that way. In fact, I wonder, this is actually a reflection across the line negative x, isn't it? Well, we'll deal with that later. So with that in mind, that's what our graph should look like. So if we're approaching the limit as, or if we're taking the limit as x approaches negative 6 from the left side, we should be looking in that direction, and it looks like this limit, as x approaches negative 6 from the left side of d of x, is going to be equal to negative infinity. So it's doing the opposite signed thing from what we had before. Now be careful, don't get too excited and just go, oh, I'll just put a negative in front. Like, yeah, that seems to be kind of what happens, but I could have asked you, what is the limit as x approaches negative 6 from the right side, in which case we wouldn't have had any information, because we don't know what's happening over here. So unfortunately, you can't do that every single time, but for odd functions, we do have the ability, and we just did and put it into action. Likewise, we also have even functions. So just like before, it says right in question 13, this one says let e of x be an even function. So as a reminder, if e of x is even, that implies that e of negative x, so if you plug in the negative of an input, you should just get the value of the function at the positive version of the input. So you could try to reason your way through here, but once again, we're going to have to be careful. So and again, we're not asked for a justification or an explanation, so I'm going to simply sketch this out. So we are told for this function e of x that is even, that the limit as x approaches negative 2 from the right side is negative infinity. So, excuse me, there's negative 2. We're approaching from the left side and going downward. So let's sketch in that way. We're interested in the limit as x approaches 2 from the left side of e of x. Oh shoot, I screwed up, didn't I? Pardon me. I drew this the limit as x approached negative 2 from the left side, but it's supposed to be from the right. So we'll do something like that. That way it's going, the function is going down towards negative infinity as we approach from the left side of, or right side of negative 2. Now we're curious about the limit as x approaches positive 2 from the left side. So first of all, here's that asymptote. Since it's even, whatever happens over here has to be exactly true over here. I mean, just think about the classic even function, the parabola. Totally symmetric about the y-axis. So if that happens there, this has to happen over here. And as we approach from the left side, it appears that this limit is also equal to negative infinity. So even functions are symmetric, so these behaviors should match, at least if we're describing the proper region. We can see that in this case, our graphical approach was probably the best way to attack. Just a little bit easier to wrap your mind around, and a quick sketch actually answered almost everything for us. Okay, that brings us then to question number 14, which starts talking about limits that have a value of infinity or negative infinity, and how to evaluate those limits. So I believe I'm attacking not every single one. I think I have 3 of them. Yeah, I have A, E, and F. So let's start with question 14a. So first, once again, question 14a tells us that the limit as x approaches 6 from the right side of f is infinity, and the limit as x approaches 6 from the right side of g is negative infinity. So if you needed to, you could draw some sort of quick little behaviors here and say something to the effect of 6 from the right of f. So, oops, it's supposed to go to positive infinity. And on the other side, we could say as x approaches 6 on the right side, we go to negative infinity. So we have those 2 different behaviors. Now we want to answer some questions about some functions that involve f of x and g of x as x goes to 6 from the right side. So in looking here, I'm going to be super precise about this and try to show every step properly. Keep in mind that you may show a little bit less work and still be able to get the correct answer, particularly in a multiple choice context. But for now, I want to be as accurate as possible. So first thing is we are trying to evaluate the limit as x approaches 6 from the right side of 5 over g of x. So if we're going to evaluate the limit of a function over another function, so long as that denominator isn't equal to 0, we can use the quotient property of limits and write this instead as the limit as x approaches 6 from the right side of 5 divided by the limit as x approaches 6 from the right side of g of x. Now in evaluating these limits, the numerator is a constant, so the value is constant. It doesn't matter where we approach 5 from, we still get 5. The denominator, though, we were told in our initial problem that that limit is equal to negative infinity. So we're dividing 5 by a humongous, like unfathomably large but negative value. So I always think about this in terms of pizza. If you have 10 people eating a pizza, the slices are a lot smaller than if you have 4 people eating the pizza. So in this case, if we're dividing that pizza into infinity slices, whether positive or negative, this is going to have a value of 0. It just keeps getting smaller and smaller. And in fact, you probably already know that. But just to remind you, there it is. I really like this step. Again, I feel like it's me being a little bit more precise than maybe necessary, but up to you. Good form for sure. That brings us next to 14e. I felt like the other questions in that section were pretty straightforward. So in 14e, we're asked to evaluate the limit as x approaches 6 from the right side of f of x plus g of x. So using the limit properties, you would likely approach this as the limit as x approaches 6 from the right side of f of x plus the limit as x approaches 6 from the right side of g of x. So you're just using the sum and difference property of limits. Well, according to what we were told, this becomes infinity plus negative infinity. Now I know the temptation is to go 0, but unfortunately, infinity plus infinity, or more specifically, infinity minus infinity, is it's not as simple as just the classic arithmetic of x minus x is 0 in this case. So in fact, in this situation, we cannot know, at least based on the information we were provided, just that their behavior was infinite in nature. It cannot be determined whether or not what the value of this limit is equal to. And in the problem set solutions, the written ones, I gave a couple examples that illustrate this idea, but for the sake of being here, I wanted to illustrate the same thing for you. I wanted to talk about that. So why is it that we can't determine this particular piece? So let's pick a couple functions that meet this expectation. So first I'm going to choose f of x is 1 over x minus 6. Let me make sure that this does go, as we approach 6 on the right side, it does go to positive infinity because you're putting in like 7, 6.5, yeah. And then for g of x, I want it to go to negative infinity at the same place, so I'm going to let g of x equal negative 1 over x minus 6. So now there are 2 functions. This one's limit, as x approaches 6 from the right side, that limit is equal to positive infinity. And this limit, as x approaches 6 from the right side, is equal to negative infinity. In fact, if you don't believe me, let's do a quick little check up here. I'm going to change these names really fast. I'm going to need those later, but whatever. Okay, so I wanted to talk about f and g. We have f of x equals 1 over x minus 6. and we have g of x equals negative 1 over x minus 6. Okay, so looking at the function, we're interested in what's happening as x approaches 6 from the right side. So on the red one, we're going to positive, blue one, we're going to negative. Now, of course, if we take the limit of these two functions together, so if we combine these two, the limit as x approaches 6 from the right side of f plus g is going to, here, I'll do it properly, f of x plus g of x. That limit is going to be equal to the limit as x approaches 6 from the right side of 1 over x minus 6 plus negative 1 over x minus 6, which those two things zero out, which means this limit is equal to 0. That would suggest that, hey, I was lying. You get 0 every time. But here's the thing. Let's make a couple small switches to our function here. Let's instead, for the moment, take a look at this function. We'll let f of x stay exactly the same, so it stays going to infinity. But for the second one, let's do negative 1 over x minus 6 squared. In this case, if you still go, it still goes to negative infinity. In fact, let's go over and look at our picture, and I'm just going to put this in parentheses and squared. So notice nothing really changed on the right side, because again, we're only interested in what's happening as we go to 6. So with that in mind, the question becomes, what happens when we do the limit as x goes to 6 from the right side of f plus g? In this case, what happens is you get this function that we're suddenly interested in. 1 over x minus 6 minus 1 over x minus 6 squared. So let's look at the graph online and see what this actually does. So we're interested in what's happening at x equals 6. There's our vertical asymptote we're interested in. We want to look at f of x plus g of x. So in looking here, if we look at what happens as x approaches 6 on the right side, shoot. This time, the limit is equal to negative infinity. So what we've just shown is in one situation we get 0, in another situation we get negative infinity. That means that we don't know enough information for us to be able to tell what this limit is actually equal to. Basically, this limit depends on the types of functions we have. And you've probably heard before, if you've seen the movie The Fault in Your Stars or studied advanced mathematics, that there are different kinds of infinity. In these cases, these are actually similar magnitude infinities. They both are countably infinite if memory serves. But with that said, one is faster growing than the other, so one has greater magnitude than the other, which means sometimes the value is 0, sometimes the value is finite, sometimes the value is infinite. So interesting question, just one of those things. It's a common misconception that this is always equal to 0, but that's not always the case. So watch out for future true or false questions. Okay, finally, 14F is the other question I wanted to look at in this section. This is just a cool question. I just think it's a really neat one to look at. It's one that can be kind of mess with your mind a little bit. So once again, though, let's jump in. We want to evaluate the limit as x approaches 6 from the right side of 3 to the g of x power. So in here, since g of x is not going to 0, or actually there's no issue here, 3 to the power is always defined for all values, all real values. So in this case, I'm going to rewrite this as 3 to the limit as x goes to 6 from the right side of g of x power. Now looking up there, we were told that that limit is equal to negative infinity. So that means we have 3 to the negative infinity power. And that can kind of mess with people. A lot of people want to just say that that's equal to infinity. But not so fast, my friends. 3 to a negative power is the same thing as 1 over 3 to the positive version of that power. And if you take 3 to the infinity power, that's like multiplying 3 times itself an infinite number of times. That's going to be a big number. In fact, I dare say that that's infinity. And if our value is now 1 over infinity, that means we're going to get an ultimate value of 0. So interesting thing to think about. Very interesting. Let's go see really fast if this actually shows up on Desmos. I've never tried this example before, but let me just see if this goes. So we were interested in the function, what's happening as we do y equals 3 to the g of x power. And around x equals 6 was what we were interested in, and look at that. It literally tells us that the value is equal to 0. So pretty interesting that it works out that way. Very cool to see. But there you go. So it did work out, and we've taken a look at some interesting infinite limits in this section. Okay, that brings us next to question number 16, which isn't really a question, it's about a statement. It asks us to determine whether each statement is true or false and explain your reasoning in either case. And in this first example, as well as the second example, I think it's 16 and 17 are the questions in question, the statements in question. The biggest key that you can use is to think about how you can disprove a statement is true always, and that is by finding a counterexample. What we want to find an example that proves that this isn't always true. Remember, it's not mathematically rigorous. It's not actually proof to find a single example that works. That's like saying, a certain machine is not defective just because you used it once and it worked just fine. It can be defective lots of times. That one single example doesn't prove anything. But one bad time does prove that the opposite is true and that it's not always a functional machine. So in this case, what we've got is a statement that reads, if p of x is a polynomial, then f of x equals p of x over x plus 4 has a vertical asymptote at x equals -4. So if that's true, it's going to be hard to prove. But if it's false, what we'd be looking for is we'd need some function that's a polynomial, p of x. That means f has no vertical asymptote. So we're on the lookout for one of those counterexamples. So the question is, can you think of a function that we could put in there for p of x that would make it so there's no vertical asymptote at x equals -4? And I'm hoping that the answer is yes, absolutely you can. Think about how we define vertical asymptotes versus holes. Holes happen when the numerator and denominator both simultaneously go to 0, whereas a vertical asymptote happens when only the denominator does. So if we want to make this so it doesn't have a vertical asymptote, we need to make sure that both the numerator and denominator go to 0 at the same time, specifically at x equals -4. So we could state, as simple as this, let p of x equal x plus 4. If p of x equals x plus 4, then f of x is equal to x plus 4 over x plus 4, which implies f has a hole at x equals -4. And if there's a hole, that means there's not a vertical asymptote, and that's a really amazing thing because it means that the statement is false. So with these statements like this, it's important to think about all the different examples you've seen. You've been prepared for lots of these things. A statement like this one you're prepared for every single time we talk about vertical asymptotes or ask you to evaluate limits or find discontinuities. It's as simple as just thinking of a single example that could work. Now, of course, you don't have to use x plus 4, by the way. You could use x squared minus 16. You could use 2x plus 8. You could choose some much more complicated polynomial, x plus 4 times 2 to the x plus log of x plus 19. There's lots of options that you could choose. The important thing is that they produce a factor of, p of x has a factor of this thing. So oftentimes you'll see in other examples or other answers that are in here, the alternate would be if p of x is a multiple of x plus 4. This is kind of the more conceptual and verbal explanation. P of x is a multiple of x plus 4. F has a hole, not a VA, at x equals -4. So that would be an okay explanation too. I believe I did kind of a combination of both on my written solutions. But there it is. Remember, when you're trying to disprove a statement or thinking about disproving a statement, see if you can't find a counterexample to show that it's not true. And with that in mind, it brings us to, I believe, our final question. That final question, or final statement, is another true-false one where we're asked to explain it. It says, let f of x equal 3 over x minus 11 when x does not equal 11. Interesting, it's one of those general behavior type limits. Keep that in mind. Then it says x is equal, or y is equal to 27 when x is 11. Does f of x have a vertical... Oh, this isn't true or false, is it at all? It just asks us to explain it. Okay, cool, I can do that. Does f of x have a vertical asymptote at x equals 11? Explain your reasoning. So the question is, do we have a VA there? Let's see. So of interest to us would be evaluating the limit as x approaches 11 from the left side or the right side of f of x. Because remember, by definition, a vertical asymptote occurs where the limit from one or the other or both sides goes to plus or minus infinity. So in this case, if we evaluate this limit as x approaches 11 from the left side, we're interested in what's happening in general as we approach 11, which means we're going to use the general portion of the function, the general behavior portion. Oh, you know what, by the way, I think I'm going to transform this back into a true or false question when I'm done, just to make sure it's fits into the section. Changed the way, but whatever. So if we do that, we want to look at the general behavior, as we've done many times before. So we ignore what's happening specifically at that one single point, and that means we're actually evaluating the limit as x approaches 11 from the left side of 3 over x minus 11. Now this doesn't take a whole lot to graph. If we look at 11, and we want to plug in, or we want to see what happens as x approaches 11 from the left side, so smaller numbers, we'd have smaller numbers, so like 3 over 10 minus 11 negative, so we'd have negative values, which tells me that this would be approaching negative infinity. So with that in mind, we've already satisfied the definition of vertical asymptote. We need the limit from one or both sides to go to infinity or negative infinity. We just did. That tells me that's enough for us to say that there is a vertical asymptote at x equals 11. So for our purposes, that's the answer we're looking for. Might change it so that the answer is true or false. We'll see when this finishes. But then that still presents a kind of awkward issue. Even if you graph that other side, while you might be able to say like, yeah, I can see the asymptotic behavior, there's still the issue of having that random point there, which for our purposes we can scale and say that it's like right there. So what about the fact that we have 11, 27 sitting there? What does that do? Does that affect anything? And the answer is no. That one point, just like always, does not change anything about the general behavior of the function. And more importantly, that single point doesn't change the fact that the behavior around 11 is asymptotic. So even with a vertical asymptote, if there happens to be a y value there, as long as the behavior of the function around it happens to approach plus or minus infinity, we still have a vertical asymptote by definition. And in fact, if you look at the picture or graph of this on Desmos, I graphed it earlier, or I put it together earlier. I called it h, remember we changed some stuff. Here's our function, just so you can kind of see it. There it is. We have that 27 there. So here, if I make this window look a little bit better, let's go 10.5, let's go 11.5. So there's our function. We'll zoom out a little bit. Notice that for sure this graph is appearing to go up to positive infinity and down to negative infinity as we look. That single point just is kind of floating there. It's kind of creepy, honestly. But it's just kind of floating there. It doesn't actually change anything. It definitely doesn't change the asymptotic behavior happening around it. There's way more points going to one of the infinities than there are points just sitting there at 27. So with that said, hopefully that clarifies the final question on the assignment 18. Hopefully this has been illuminating and helpful to you. Thank you as always for watching.